welcome back. In this session, we will discuss about rolling loads and concept of influence lines diagram. We know that most common loads acting on the structures are dead load and live load. Sometimes there are conditions in which loads can be moving across a beam. For example, consider this bridge A, B, C, D, E, F. This bridge is supported on A and F. There are two pillars or columns B, G, and D, H. And consider one vehicle is moving from this left side to right side, okay, across this bridge. In this condition, this live load is moving from A to F. So if we want to calculate shear force or bending moment or reaction, we can see that the position of the load is moving from left to right. So for each position we will get new values of shear force, bending moment, and reactions. So if you want to calculate or if you want to design this pillar BG, we should find the maximum reaction acting at this pillar. For that, we will find the position of this vehicle. For that, we will get maximum reaction. This type of loading is known as rolling loads or moving loads, and the method we are using for calculating the position of this maximum shear force or reaction or bending moment or these factors shear force or bending moment or reactions are known as influence line diagram concept. Next, influence line diagram. Actually, influence line diagram is a graph showing for any given section of a beam the magnitude and character of some function, that is magnitude and character of shear force, bending moment, and reaction for all position of a moving unit load. Note that moving unit load as it crosses the beam from end to other. That means, for example, if you in this example, if you want to calculate the maximum shear force at any point, say at this section, shear force and bending moment and maximum reaction acting at this pillar, then we will move one moving unit load from one end to other. Okay, then we will plot one graph. We will get one graph. That graph is known as influence line diagram. And by using this graph, we'll find out the shear force, bending moment, and reactions. Here, a unit load means it has a magnitude of 1 unit, but no dimensions. Note that it has no dimension, but magnitude of 1 unit. The variation of ILD or influence line diagram for statically determinate structures is linear, and for statically indeterminate structures, the variation of ILD is a non-linear graph. Also, shear force or bending moment or reaction from the ILD due to point load equal to ordinate under the load into load. I will explain this with an example. And also shear force or bending moment or reaction from influence line diagram due to UDL equal to area under the load into load. Now ILD for statically determinate structures. Consider a simply supported beam and there is a load of 1 kilonewton acting at a distance of x1 from the support A. We are going to derive influence line diagram for this beam. Influence line diagram of reaction, shear force, bending moment for this beam. Now first in ILD for reactions at A and B. For drawing the ILD for reaction at A, we'll push this support A by 1 unit. Okay. Then this magnitude is 1, and when you are pushing this end, as this end is hinged or roller, it won't move, so we'll get a triangular shape. This is the ILD for RA, and this end is having a magnitude of 1 unit. And if you want to calculate ILD ordinate at a distance of x1, at a distance of x1, if you want to calculate this ordinate from similar triangle, you will get 1 by, you will consider this triangle and this small triangle. So for this triangle, 1 by length of beam is L equal to this ordinate you want to calculate. Let it be ordinate O. Okay, this is O. 1 by L equal to O by and this length. Okay, if this length is x1, then this will be L minus x1. So O by L minus x1. So this ordinate O equal to L minus x1 in x1 divided by L. That is L minus x1 divided by L. Now we know that for shear force or bending moment or reaction from ILD due to point load will be equal to ordinate under the load into load. In this case, at section x1, ordinate is L minus x1 divided by L, and magnitude of load is 1. So we'll get RA equal to ordinate under the load into load equal to L minus x1 by L into 1 equal to L minus x1 by L. Similarly for ILD for RB, we'll push RB by 1 unit, then we will get a triangle. This is the shape of ILD for RB. Here also RB will be equal to x1 by L. Now ILD for shear force at C, at any section C. Consider the same beam AB. We want to calculate shear force at a section X, that is at point C at a section X. For that, assume load is left side of C. First you will assume this is section C and the load is acting at left side of C, that is here, and analyze from the right side. Analyze from the right side means from this side. So shear force will be equal to shear force at C. Okay, shear force at C means algebraic sum of forces either to the left or to the right. In this case, you are considering the right portion only. Okay, so right portion means only one load RB. So you'll get the value of shear force at C equal to RB, and there will be a minus sign because the sign convention for shear force is left side upward positive, right side downward positive. Okay, this is the positive sign convention. Here right side upward, so negative. So shear force at C equal to minus RB. Now we are assuming load is at the right side of C and analyze from the left side. Then we'll get only one load is acting at left end, so we'll get shear force at C equal to RA, left side upward, so positive value. Now if you want to calculate or if you want to draw shear force at C, we need to combine these two cases. Because this is shear force. In this case, force is acting just left side of C. Second case, force is acting just right side of C. So if you are combining these two cases, you'll get the shear force at C. Okay. For first case, this is the first case. Load is acting left side of C. We'll draw RB. RB means this is RB diagram. Okay. So for this load is acting this session, we'll draw RB diagram. Okay. This is negative value. So we are drawing below this axis. So RB diagram. Value of RB magnitude of RB will be x by L. Okay, ordinate of RB will be x by L. So we'll draw like this. This is x by L. This is a negative value. Okay, RB equal to this portion, this ordinate is x by L, and we will get a triangle. And now for the second case, when the load is acting right side of C, load is acting right side of C. In this case, Ra is the shear force. So in right side, we'll draw Ra. Ra means this is Ra. Ordinate of Ra will be L minus x by L. So this is L minus x by L, this ordinate. Okay. So shear force, ILD for shear force diagram will be like this. Okay, for any section, if this is a beam and if you want to draw ILD at this section, okay, we'll draw like this. This is, if this is x distance, then this is x by L. This is x by L. See, x by L. This is negative value and this is positive value, and this is L minus x by L. See, L minus x by L. This is the sign convention for shear force. Now ILD for bending moment at C. For deriving the ILD for bending moment at C, first assume load is left side of C and analyze from the right side. Okay. Then bending moment will be force RB into this distance. Okay, RB is x by L or x1 by L into this distance is L minus x. This is x, so this is L minus x. Similarly, assume load is right side of C and analyze from the left side. Then Ra into x. Ra into x means Ra is L minus x1 by L. Then Ra into x means L minus x1 by L into x. Now if you are combining these two figures, you'll get a triangle. That is a triangle with the maximum ordinate L minus x into x by L. Okay, we are combining these two, L minus x into x1 by L and L minus x. These cases will get this value. Okay, so ILD for a bending moment will be a triangle. Okay, for any beam, for any beam at section x, at section x. This is a triangle. ILD for a bending moment will be a triangle with the maximum ordinate L minus x into x whole divided by L. Now example 1. Consider a simply supported beam AB which has a span of 5 meters. Draw the influence lines for RA, RB, shear force at X, bending moment at X for a section X at a distance of 2.5 meter from the left side or left support. Okay, we have a beam AB, simply supported beam, and there is a point load of 20 kilonewton at a distance of 2 meter, and we are asked to find out the shear force, influence line for shear force, bending moment and reaction at A and B at a section 2.5 meter. Okay, total length of the beam is 5 meters. Now this is the figure. Beam AB, load at 2 meters, section at 2.5 meter. Okay, so in this case x1 equal to 2 meter, x equal to 2.5 meter, length L equal to 5 meter. Now first ILD for RA. ILD for RA will be like this. We are pushing this support A by 1 unit, so it will be a triangle. Okay. Now ILD for RB will be like this. Okay, we are pushing B, and we'll get triangle with the magnitude of maximum magnitude 1 unit. Then ILD for shear force. This is a section at a 2.5 meter. So shape will be like this. With this is negative portion, this is positive portion. Negative will get x minus x by L, and this ordinate it is L minus x by L. Now ILD for bending moment is will be a triangle at maximum ordinate at x, that is 2.5 meter, and the magnitude of ordinate is L minus x into x divided by L. Okay, for all the simply supported beams this will be the case. Now we want to find out reaction RA. Okay, this is a simply supported beam, 20 kilonewton load at 2 meters. So any shear force equal to shear force or bending moment or reaction equal to ordinate under the load into load. So in this case RA equal to ordinate under the load of the ILD of RA into load. Okay, so this is the ILD for RA. Ordinate under the load means this is the load 20. So we want to find the ordinate. Ordinate means this value under the load, that is at 2 meters. At 2 meters, what is the value of ordinate? Okay, from the similar triangles means from this large triangle and this small triangle. Okay, 1 by this is 1 by total length L 5 equal to this is ordinate O1 divided by this length is 3, total length 5, this is 2, so 5 minus 2 equal to 3. So ordinate O1 will be equal to 3 into 1 divided by 5 equal to 0.6. Okay, no need to write any unit here, just magnitude 0.6. This is the ordinate under the load 0.6, and load value is 20 kilonewton. So 0.6 into 20 kilonewton will get 12 kilonewton as the reaction. You can check using other methods or equilibrium equations. You will get 12 kilonewton as the reaction at A. Now to find out reaction at B, we'll draw ILD. This is a triangle with a maximum ordinate 1. Now RB will be equal to ordinate under the load into load. This is our load. So ordinate under the load means this value. Say it is O2. So from but similar triangles means this triangle and this small triangle. Okay, 1 by this is 1 by total length 5 equal to O2 by this length. Total length is 5, so this is 2. This is 2. So O2 by 2. O2 will get 0.4. So ordinate under the load is 0.4, and load will be 20 kilonewton. So RB will be equal to ordinate under the load into load equal to 8 kilonewton. Now to find out shear force at a section at a distance of 2.5 meters. Okay, first we will draw ILD. ILD will be like this. This is negative portion, this is positive portion. This ordinate is minus x by L, and this ordinate is L minus x by L. Okay, minus x by L means x equal to 2.5, so minus 2.5 by 5 equal to minus 0.5. L minus x by L means L is 5, 5 minus x is 2.5, 5 minus 2.5 divided by 5 equal to 0.5 plus 0.5. Now shear force at x, that is at 2.5 meters, equal to ordinate under the load into load. Ordinate under the load means this is load. Ordinate under the load means ordinate at 2 meters, that is this is the ordinate under the load O3. Okay, so we'll consider only these triangles to find out this ordinate. From similar triangles, this triangle and this small triangle. This is zero point 0.5 minus zero point 0.5 divided by 2.5 equal to, this is ordinate O3 divided by 2. You will get ordinate equal to minus 0.4. So ordinate under the load is minus 0.4 into load 20. You will get 8 kilonewton. This is the shear force at X. Now bending moment. To find out bending moment, we will draw bending moment ILD for bending moment diagram. At a section x meters equal to x equal to 2.5. This will be a triangle with a maximum ordinate L minus x into x by L. L minus x into x by L means 5 minus 2.5 into 2.5 by 5 equal to 1.25. This is 1.25. Now bending moment at x equal to ordinate under the load into load. Ordinate under the load means this is ordinate. This is load. Ordinate under the load means this is ordinate of 4. So from these two triangles, this triangle and these triangles, you'll get this is 1.25. 1.25 divided by 2.5. This length is 2.5 equal to, this is O4. O4 divided by 2. This length is 2. So O4 equal to 1. No unit or magnitude is 1. So bending moment equal to ordinate under the load into load equal to 1 into 20 kilonewton. So value will be 20 kilonewton meter. Don't forget to put the unit for bending moment. This is kilonewton meter. Okay. This is the procedure for calculating shear force, reaction and bending moment of a simply supported beam using the concept of ILD. Don't forget that shear force or bending moment or reaction from ILD due to point load equal to ordinate under the load into load. Okay. Then shear force or bending moment or reaction from ILD due to UDL will be equal to area under the load into load. Now, how are influence lines useful or uses of influence line? To find the values of shear force, bending moment at the section when any system of loading is acting on a system beam, like this example. To find shear force, bending moment and reaction, we will use influence line diagram. Next, to find the position of a loading system under which a function like shear force or bending moment is maximum at a section. So if you want to calculate maximum value of shear force for a certain position, we can find that position also using influence line diagram. This we will discuss later. Thank you.